Hi everyone. We're moving on to the probability topic today, and we're going to start by looking at Venn diagrams. I'm sure you will have seen them before at GCSE and before that as well. To be honest, a lot of it you probably will know already, so quite a lot of recap here. But there are some new things to learn about, and we're specifically, the most important bits to talk about today are mutually exclusive events and independent events, and we'll talk about those later on. So this is what we're going to cover. We'll talk about events and how Venn diagrams work and the universal set, which you might not have heard of before. So it's just a little bit of new notation and new language, basically. A bit about probabilities, how we get probabilities from the Venn diagram, and then we'll finish off with what we were saying before about mutually exclusive events and independent events and why they're so important. And as always, we'll throw an exam-style question in at the end so you can see what you'll be up against at the end of the year. Okay, so events in the universal set. Here is a Venn diagram. Not a very exciting one, but a Venn diagram nonetheless. So our labels here, A and B, are events. Okay, so A is an event. It could be anything. A just represents it. Maybe it's people who play football or people who watch TV more than 4 hours a day. It can be anything you like, okay? Any event you like. B is another event. Okay. And on Venn diagrams, we show events as circles. And in those circles, we put either the probability of being in that circle or the number of people that fall into that category. Here we've got an overlap between events A and B, and those are the people where they do events A and event B. So they do both those things at once. This big rectangle on the outside is what we call the universal set. It represents everything, and things that people or things that don't fall into A or B go on the outside. So on the outside we have people who don't do A or B, or people who don't fall into A or B. Yeah, so this is referred to as the universal set. And inside the universal set is everyone that we're considering. And it gives us space to put people who don't fall into any of the events, but we're still kind of looking at, we're still considering. So they just go on the outside of the circles, but still inside this rectangle. Okay, so something you probably already knew, all probabilities sum up to 1, and we can use that to help us complete Venn diagrams a lot of the time. So here we've got a Venn diagram with two events, A and B, and it's got probabilities in. So there's 0.35 people in A who don't do B, there's 0.1 who do A and B, and there's 0.45 or 45% of people who just do B. So how many don't do A or B? Well, it's dead easy. All we do is we add all these probabilities up that we know so far. And we get 0.9. So we know there's still 10% of people on the outside who don't do A or B, okay? So we can fill that in with 0.1 using the fact that all the probabilities sum to 1. Okay, so nice and straightforward. We can complete Venn diagrams using the idea that the universal set contains everything. There's probabilities have to sum to 1 inside the universal set, so we can finish off missing probabilities. Here's another example, slightly more complicated Venn diagram. We've got the number that's on the outside, 0.05, and we've got the probability of A, we've got B by itself and C by itself, but not the probability of B and C. It's the only probability that's missing, so by adding all these up, we can find what that probability should be. So if we do 0.2 plus 0.05 plus 0.3 plus 0.25, that gives us 0.8. So we know they have to add up to 1, so we know there's 0.2 missing, okay? So that in there should be 0.2, okay? Again, using the fact that all the probabilities sum to 1 to find missing entries in Venn diagrams, and we'll do that quite a lot in exams as like part A's of questions. So this is a little bit more about probabilities, and I've just brought in one of the Venn diagrams from the previous section, and we're going to work out some probabilities. Now we write probabilities like this most of the time. So P means probability, okay? So on that first line I've written there, it means probability of A happening, okay? Now, a lot of you are probably thinking, well, probability of A, that's 0.35. It's not. Probability of A is everything inside A. I'm going to write that there because it's something people often forget. It's everything inside the circle A. Okay? Everything inside that circle. And you can see both this and this are inside A. So actually, the probability of A is 0.35 plus 0.1, which is 0.45. Okay, we have to include the people who do A and B because they do A, okay? And that's what we're asking, the probability of people doing A. Probability of B, the exact same logic applies. It's not just these people, it's the people in the middle still because they do B as well. So we've got 0.45 plus the 0.1, it's 0.55. And what about the probability of A and B? Now those are the people in the middle. That is the probability of doing A and doing B, okay? So that is 0.1, the intersection. We call that the intersection between A and B. You don't need to know the technical names, but you don't need to know that it's the intersection. But we're looking at the people who lie in both the circle A and B there. Now, probability of A or B. So when we say or in statistics, we mean doing A or doing B or doing both. When we say or, it can include the people who do both things as well. It's not they can just do this or that, okay? They're allowed to do both as well. So actually, for the or, these people do A or B, these people do A or B, and these people do A or B. They actually do both of them, okay? So we add up everyone who does A or B. So that's going to be 0.35 plus 0.1 plus 0.45 is 0.9. And there's actually an easier way of doing that. We could say, well, the only people that don't do A or B are these people on the outside. Okay, so if we do 1 minus 0.1, because they're the only people that don't do A or B, we get 0.9. Okay, so that's the probability of it doing A or doing B. If it says the probability of doing A or B but not both, then we wouldn't include these people in the middle. Okay, we wouldn't include these people, and it would just be 0.8. Okay. So let's have a look at some more probabilities. So a more complicated Venn diagram this time with 3 events and 2 overlaps. So we're going to work out a few things here. Here's the first few. Probability of A, remember, I'm going to write it again just so you remember. Everything inside A. It's such a common mistake that examiners see over and over again that people just write that. Okay, it's everything inside A. It has to include these people as well because they do A. Okay, so it's actually 0.29, this one. I've added together the 0.21, the 0.08. Probability of B, I have to include those people and these people as well. It's everything inside B. And that gets us 0.41. Or 41% of people. What about the probability of B and C? Well, that's just these people in the intersection here between B and C. So that's 5% of people, or 0.05. A or B, that's the people that are in A or B or in both. So that is this one, this one, this one, and this one. Okay, it includes people that do A and B. In fact, the only people that aren't included are the people just in C and the people on the outside, which we haven't figured out yet. So if we add all those up, we get 0.21 plus 0.08 plus 0.28 plus 0.05, which is adds up to 0.62. And we've got a few more to work out as well. So the probability of not A or B or C. So these are the people that aren't in A or B or C. Okay. So these are actually just the people left on the outside. To figure out what that is, we can do 1 minus all those probabilities, because the only people we haven't filled in yet are the people on the outside. These are the only people we don't know. So if we do 1 minus all these people, so we know it has to add up to 1, we'll get the answer. So I'll stick that in the calculator. And I get 0.13. Okay, so that's 13% of people who don't do A or B or C, don't fit into A or B or C. What about the probability of A and C? Trick question, this one. A and C, there's no overlap, is there? They never overlap each other. They both overlap with B, but A and C never overlap. So there's 0% of people in there. No one does A and C. What about A or C? This is anyone that's in A or C. These people are in A or C. This is still in A. This is in C. And this is in C. Okay, so we've got 0.21, 0.08. Those are the people in A. We also add the people in C, which are those people. And that gives us 0.3151, 0.59. Okay. And that is all the probabilities I've asked for this one. We've done quite a few there. Hopefully gives you an idea of all the things you could possibly be asked. And just making sure you add the right probabilities together. All we do is add the probabilities of everyone who fits the criteria for the event we want to look at. Okay. So here's another style of question. Instead of giving you a probability, I've just given actual numbers of people this time. And we're going to find a few things. So we've got the probability, or sorry, not the probability, the number of people who do athletics, the number of people who play badminton. Some play both or do both, and there's 30 students altogether. Okay. So we want the number of students who take part in, who don't take part in either. These are the people on the outside, aren't they? So this is the number of people who don't do athletics or badminton. Well, we know they add up to 30. Yeah, so if I do 30 minus 13 minus 2 minus 6, that'll leave me with how many don't do either, which is 9. Okay? Because I know there's 30 students in that class. It's told to us in the question. And we're going to work out some probabilities here. So we want the probability of A first of all, which is athletics. I've just shortened it to A. Well, how many people do A? These people do, and these people do. But so there's 15 people that do athletics. So 15 people out of the 30 in the class do athletics. So if we randomly pick a person in the class, there's a 15 in 30 chance they do athletics. 15 in 30 simplifies to 0.5. Okay, so there's a 50% chance that they do athletics. What about the probability of doing athletics and doing badminton? Well, the only people who do both are those two people. So it's 2 out of a possible 30. So if we pick a random person, there's a 2 in 30 chance that they do both. And we can simplify that to 1 in 15. Okay, so I'll not write that as a decimal because it's it doesn't stop. It's an irrational number. So probability of A or B, that's everyone who does athletics or badminton. So it's these people, and these people. If we add those up, that's 21. 13 plus 2 plus 6. It's 21 out of 30. So there's a 21 in 30 chance that if you pick a random person, they would do athletics or badminton or both. And that simplifies to 0.7. Okay, and that's all the probabilities I've got for that example.